In last lesson, we learned how to use matrix to represent the linear transformation. And today we're going to learn inverse transformation and how to use the inverse matrix to express inverse transformations. Particularly, we're going to look for a few concepts besides the inverse transformation and the inverse matrix. We're going to look for determinant and the procedure to find the inverse matrix. In the first lesson, we learned a significant difference between matrix algebra and the college algebra. The matrix algebra is non-commutative. That means if you multiply A to B, most of the time it will not equals B to A. So today we're going to first observe some algebraic property. For example, A, whatever number times 0, you still get 0. And A times 1, you still get A. And the third property, if A times B equals 0, then either A equals 0 or B equals 0. So we're going to see if these properties are all true. First, let's define the counterpart of 0 matrix. Today we all focus on square matrix. That means the row always equal the columns. So if we have a 2 by 2 matrix, if you put all elements as 0, we call this as O, capital O. That's 0 matrix. 0 matrix. In 3 by 3 dimension, you just put 9 zeros. Again, that's a 0 matrix. And then if you have any matrix, multiply this 0, very easy to check because all the elements is 0, you're going to get a 0. Anyway, so the first property is the same. We're going to define the counterpart of identity 1. We call it I. All you need is put the major diagonal as 1, and then all the other elements are zeros. So again, we can do the multiplication. We can find that A times I equals I times A always equal A. So in that sense, the matrix and the linear algebra are the same. 1 times A equal A, I times A equal A. So the I plays the role of the constant 1. And the O matrix plays the role of the 0 in algebra. Well, let's see the third property. We're going to look at an example of our projection transformations. So in this example, I have 2 transformations. This F is going to project the X, any vector X here, onto the vector V, which is 1, 2, 2. We're going to do this projection here. So this is the first Fx. And the second Gx, we're going to project this X vector into the plane. This plane equation is x plus 2y plus 2z equals 0. I believe we discussed these two matrices before. So the transformation matrix to project the X to V is this A. Now if you look, it's a symmetric matrix, and all columns and the rows are parallel to this V vector. The second matrix, we won't go to detail. How do we get it? We just pay attention. The normal vector of the plane is n equals 1, 2, 2 is the same as the V. So in other words, this V is precise the normal vector of the plane. So to project the X to the plane, all I need is subtract the X to the projection fx. We did this in last lesson, so I'm not going to repeat. So we get the B matrix as the projection to the plane as follows. The B is this: 1/9, 8, -2, -2, and that's what you get for the B. So now I got a 2 3x3 matrix. None of them are 0 matrix. Let's do the multiplication. Well, I'm not going to check every element, but let me do a few. Let me do the first one. First row, first column, then you have 8 plus 2 times -2 plus 2 times -2. That's 0 here. Let me go to the second row, second column. That will be 2 times -2 plus 4 times 5 and plus 4 times -4, which is -4 plus 20 minus 16. Again, you get a 0. So is this. I'm going to check one more. Let's select this one. That's the first row, third column. Then you pick the first row, third column, and we have 1 times -2 plus 2 times -4 plus 2 times 4. Wait a moment. 1 times -2, 2 times -4, and 2 times 4. I needed to check that. It's supposed to be also 0, unless I made some typo. Anyway, this is a non-zero matrix. When you multiply, they got identical to 0. So what does that mean? So that really means A times B equals 0 matrix, but neither A nor B equals 0. In other words, this property 3 is not true for the matrix algebra. So we need to understand a little more about this. Let me explain. From the geometric point of view, now you have an X, whatever vector, you first project it to the plane, and then you get the shadow of this vector on the plane. Now the second projection, you project it to the perpendicular line to the plane. That's the normal vector. Of course, in that case, this whole shadow will become a point on the line. And which is the point? the point is 0, 0, 0, the origin. So in other words, whatever x you do, if you do this way, you always get a 0. The product of the matrix we looked, it's really A times Bx if you want to do a projection. Unless the A, B always equals 0, you will not get a 0 for any vectors. So in this case, the A and the B will get the product 0, as you see from the picture. So from this example, we found in matrix algebra, A times B equals 0 does not mean A must be 0 or B must be 0. So what does that mean then? We're going to look at more examples.